Welcome, everyone. Thank you for joining us today's webinar. My name is Matthew Byer. I am the Technical Sales Representative at ThermTest, and I will be the host for this webinar. Today, Jeff Redelick will be presenting our webinar on touch times and steady-state testings of foams. Before we begin the webinar, I would like to mention our upcoming 3 webinars during October and November. All attendees to this webinar will receive an email invitation for our upcoming webinars once registration is open. At the end of the webinar, we will have a Q&A session answered by Jeff with the remaining time. Please type your questions in the chat box at any time during the webinar. If we run out of time during the Q&A, remaining questions will be answered in the post-webinar email on Friday, October 16th, along with a link to the recording. So I'll now pass along the webinar to Jeff.
Okay, thank you, Matt. And while everyone takes a moment to look at the agenda, I'd like to thank you for attending this webinar. So first, the focus of this webinar is going to be on testing foam. And you may not realize this, but foam is as common as it is necessary in our day-to-day lives. In 2018, the output of foam to the US economy was $45 billion, and this is around foam insulation. Another very large foam economy is in ergonomic foams. So this is foams used for comfort applications, like mattresses, pillows, the cushions and chairs, and things like that. Now, it's important to know your foam. You need to know the properties of your foam if you wish to design foam that is attractive to a customer. When it comes to things like foam insulation, we look at thermal conducticity, because in an application with foam insulation, you're trying to insulate a building and make the building more heat efficient. So you could use a HFM 100, which is a steady state method, which will measure thermal conductivity. In the case of ergonomic foams, or these foams used for comfort applications, the more apt property that you'd like to investigate is thermal effusivity. Now, you can measure this multiple different ways. A few of them are the TPS EFF. This is a transient plane source effusivity meter. This is a transient method. And we're excited to talk about in this lecture, or in this talk, the HFM 100 transient module. And we'll discuss that later. So it's for the rest of this talk, we are going to be focusing on ergonomic foams, their applications, and how we are going to measure them. So since we're measuring the thermal effusivity of these foams, we might as well discuss thermal effusivity briefly. Now, thermal effusivity is not a standalone property, but it's rather an expression of other properties. You see here in this equation in the middle, center left of the screen, the thermal effusivity is equal to the square root of the product of the thermal conductivity, the density, and the heat capacity. So it's an expression of those 3 properties. Thermal effusivity is the propensity for a material to exchange heat with another surface with which it is in direct contact. If we look at the graph on the right, if we were to take a measurement of a foam sample, or if we were to just apply pressure to a foam sample with our hand and touch it, you'll notice that in materials of low thermal effusivity, the temperature rise over time is higher. There is a higher temperature rise over time compared to materials of lower thermal effusivity. Since the heat is being exchanged with the other material, there's no time for a temperature rise. There's less time for temperature rise to be observed at this surface. So one application of thermal effusivity, which we will look at in this talk, is the measurement of the coolness or warmth feeling of materials. So essentially, you can attribute a number to a material for how warm or cool it will feel, and that's thermal effusivity. If you look at the image on the right, we've got 2 hands touching 2 different materials. The material on the left is a wood material, and relative to the material on the right, which is a metallic material, the wood material is lower in effusivity than the metal. So the wood will feel warmer to the touch than would the metal. In materials like bedding and foam, heat transfer mechanisms can include more than just conduction. When multiple modes of heat transfer exist, beyond solely conduction, the appropriate term becomes thermal conductance, and by extension, thermal effusence. I thought it's important to make that distinction here. For the remainder of the talk, we will be discussing thermal effusivity. So to measure thermal effusivity, we can use the transient plane source effusivity meter. This is a transient method. It is portable. You can power the system with batteries or with a USB plug-in. Is it easy to use with a convenient graphical interface on the front of the device? And it comes with a data utility that can export your results into file format that is compatible with Excel and other spreadsheet software. It's also important to note that this device complies with an internationally recognized standard of testing. A unique ability in this meter is that it features 2 and 10-second test times. Now, why would we care about this? We can gain insight on how a mattress feels to the touch for short or long test times. And this can influence a buyer who's comparing between different samples. A sample that feels more attractive to the touch, we can determine what that is through thermal effusivity. And through the thermal effusivity, you can design a product that is more attractive to the touch and the buyer is more likely to purchase. A bit more on the 2 or 10-second touch times. The effusivity of a material, thermal effusivity, will vary with different touch times for layered or non-homogeneous materials, which means that for homogeneous materials, it should not vary. It will not vary. When you use a longer touch time, the heat will be able to diffuse through more layers, each layer affecting the measured thermal effusivity. For example, if we look at is on the lower half of the screen, we first have a negative control. If we put our effusivity meter sensor on top of just this mattress foam itself, which is fairly uniform in its composition, no matter if we use a 2-second touch time or with a 10-second touch time, we allow the heat to diffuse further into the material, we obtain the same number for our thermal effusivity. If we look to the middle of these, the center of these 3 images, we introduce an active layer on top of the mattress foam. Now with the short touch time, the 2-second touch time, due to the properties of this surface layer, it has a higher thermal effusivity. We record a higher thermal effusivity for the initial 2-second touch time. As we record for 10 seconds, as we take a 10-second measurement, the thermal effusivity becomes closer to that of the mattress material. As the heat diffuses further into the mattress, we obtain a value that is more representative of the mattress itself. Another interesting case is with phase change materials. So these are materials with wax-like substances, materials that melt at around room temperature or just a bit above or below room temperature. Depending on whether the material melts or solidifies, you'll observe an endothermic or exothermic reaction upon contact with this material. For instance, this material on the right, if we apply our thermal effusivity meter sensor to this material, the heat is being absorbed into this surface phase change material due to an endothermic reaction. And even as we take a 10-second measurement, the heat continues to be absorbed into this material. And it will not be until all of the material, the phase change material, has melted that the heat will continue to diffuse into the mattress foam itself. Another method that we will be discussing for measuring thermal effusivity is the HFM 100. Anyone who is familiar with this instrument might find that a bit peculiar, because traditionally this instrument is used in a steady state method to measure the thermal conductivity, which includes 30 to 60 minute test times. This will allow us to gain insight on foam-like applications, like how does a mattress conduct heat from the body after laying on it for an extended period. What we are trying to investigate is what occurs in the period between 10 seconds and 30 minutes. We want to figure out what the user experience is in that time window compared to the bulk material properties that you'd get from the steady state method. In a paper by Tulubayev in 2017, he published this equation, which allows you to measure the effusivity of a material via a transient using this is a typically steady state instrument, but depending on the experimental setup, you can use a transient method to measure the thermal effusivity of a material. That's what we'll be talking about. So briefly going over this equation in the middle, you can solve for the thermal effusivity as long as you can track your heat flux over time, which this instrument does via a flux sensor, and the temperature difference, which the thermocouples in this instrument also track. So as long as you track these data points over time, you can calculate the thermal effusivity. We're calling this the HFM 1000 transient module. And so how this would work is, and we'll have an illustration of this later on. With the sample in an isothermal state resting on the bottom flux plate, and we set this to 20 degrees Celsius, which is room temperature, the upper plate can reach a set temperature away from the sample, and we set this to 37 degrees, which is the average body temperature. And then you can bring this upper plate down onto the sample. And so this is simulating a person interfacing with a material, which in this case is a mattress foam sample. By monitoring the flux on the upper plate over time as it is in contact with the sample, we can determine the thermal effusivity of the material using this instrument that's typically used for steady state methods. Now, it's important to note this requires a sufficiently thick sample, and it turns out that we can assume this sample is infinitely thick as long as a heat wave from the upper plate is still diffusing into the sample and has not reached the other end of the sample. So in the case of our 26 millimeter foam mattress test sample, this takes about 4 to 5 minutes. So for 4 to 5 minutes, we can record thermal effusivity. So our simulation, this is what we're trying to simulate, is a hand, it is at 37 degrees Celsius, and a mattress foam isothermal at 20 degrees. And then the hand comes in contact with this foam. How do we simulate this on the HFM? Well, we have our foam sample on the lower plate at 20 degrees Celsius. We preheat our upper plate at 37 degrees. We bring these two together, and then we begin to record the change in flux over time, as well as the temperature difference. So the goal of this experiment we performed was to measure the initial and prolonged touch time of thermal effusivity experienced by a user on a mattress. We tested on a mattress foam sample by itself, as well as the foam sample with a couple of different layers placed on the surface of the foam in an attempt to modify the initial effusivity, the effusivity of the initial touch method. We want to know how these methods compare. So the thermal effusivity is going to measure the initial touch, 2 and 10 seconds, where we use the HFM to measure prolonged touch up to 5 minutes. Due to the small thickness of the added layers, it is expected that the thermal effusivity of the different samples should converge after some time, which we should observe with the HFM recordings. What did we find? Well, I'll break this graph down a little bit. So we measured the effusivity of foam using a transient plane source effusivity meter. Now, if you look at this dotted line further on the left, the first 2 points at 2 and 10 seconds, these were recorded with the effusivity meter. And then on to the right of this dashed line, the remainder of these points were recorded with the HFM 100 transient module. And so what we found was, for the red circles with the foam, the thermal effusivity did not change with initial touch time as well as the prolonged touch time. When we add a polyester cover, which has lower thermal effusivity than the mattress foam, as expected, for the initial touch, there is a lower measured thermal effusivity, which levels out over time to the same value as foam by itself, as well as a foam with PCM cover. With our TPS EFF instrument, we note an increase in thermal effusivity until all of the material has changed phase, at which point the thermal effusivity tapers off and resembles that of the foam by itself. So we conclude that the measured thermal effusivities did indeed converge to a single value. Due to the negligible thickness of the added layers, this is why they will converge. The large thickness of the foam is what will predominate and which will be the most representative of the measured thermal effusivity. And this is not necessarily the case if we used layers that were more thick. So depending on the experimental setup, you would observe something else, which is very interesting. We'll talk about that in a second. The HFM 100 transient module is also useful when looking to quickly differentiate between two samples that are similar in appearance, but different in thermal effusivity. This will allow you to differentiate between these two types of materials in a matter of minutes, rather than 30 to 60 minutes if you were to use the steady state method of this instrument. So back to that earlier point, how would you design a foam with a lasting change in measured thermal effusivity? So a foam that feels cooler for longer. If we look at our results from before, if you were to introduce a material that was more thick and had a higher thermal effusivity than the mattress foam itself, you would observe something like this. This is an estimated, all of these lines are estimations. The higher thermal effusivity will be recorded through the initial touch time, and due to the higher thickness of this material, you will observe a higher thermal effusivity of this material as the heat diffuses through it for a prolonged period of time due to the increased thickness. As the heat diffuses through this surface layer, this top layer, and further into the mattress foam, the value will approach the mattress foam itself over time. And with that, I'd like to thank you for listening. Here are a glossary of terms. Don't forget that we have some upcoming webinars, which I believe you will receive an invitation to. It's time for any questions and answers. If you have any questions, please type them in the chat. We will try to get to them. If not, we will reply to them in an email, which will be sent later on. Thanks for listening. I guess it was just a very well-explained talk. Perhaps we don't have any questions. We'll wait a couple more minutes. If anyone has any questions, feel free to ask. Okay, we have a question. How do you know that the TPS EFF complies with the ASTM standard? So that's referring to this instrument here. It says that it complies, the second from the bottom in the properties table there, it says it complies to the ASTM D7984-16. So it complies. You'll note in that ASTM, it mentions that some sensors require a guard, and our sensor does not require a guard due to the large diameter of the sensor. Due to this large diameter and short test times, we can ensure one-dimensional heat propagation. And due to the onboard electronics recording data points required by the standard, it does comply with the standard. Okay, if there are no more questions, then we're going to leave it there. Thank you for attending this webinar, and feel free to attend any of the future webinars, and have a good morning.